Well, in this exercise, compensate the system. So we need to compensate the system whose root locus is shown in. So the root locus is, we found it in here in our previous exercise, in exercise 1. We found the root locus. Okay, so now this is with a compensator. We can take the compensator over. So basically it's the same exercise as we did before, but here compensate the system. They ask us to build a controller compensator to improve the steady state error by a factor of 10 if the system is operating with a damping ratio of 0.174. Okay, so let's start working on it. So how to start? First, damping ratio of 0.174. So that means zeta equals 0.174, which equivalent to say overshoot is, so you go to the website if you wish quickly, and here 0.174, so it gives you 57.4. 0.4%. Basically it's similar to the previous exercise, and directly I know this overshoot we obtained it when K from previous exercise was equal to how much. If we don't remember, we go to previous exercise. Let me delete this and this, and maybe that's again. So here they overshoot 57.45 at gain K equal 180. So at gain K equal 180, so my controller is equal to 180, I get an overshoot of 57.5. So this is when K was equal to 180. Alright, that's what we did in the previous exercise. At that K equal 180, I can get an overshoot of 10, and that's how it will look like my step response. So steady state 0.9. So the question is, compensate the system, find a compensator to improve the steady state error by a factor of 10. So your goal is to find a controller, C of S, for which I can improve the steady state error by a factor of 10. So means here after adding the compensator, before adding the compensator. The old is before adding the compensator, which is now. The steady state error old is the current steady state error, which is 0.9. So then, if I want to find a compensator to improve my steady state error by a factor of 10, so 0.1, why 0.1? Because 1 minus 0.9, that will be my error, over 10. So 0.1 over 10, 0.01 will be my new steady state error. Alright, so what controller I can do, I can add, what type of controller I can add that improve my steady state error by a factor of 10. So I'm telling you, when you want to improve the steady state error, when you want to cancel the steady state error, you know that we add integrator, as we did in the first exercise. We can add 1 over S, and to cancel the effect of poles at 0, I may add S plus 0.1, like 0 close to the pole, at origin, so they neglect the angle effect. So then I can add this kind of control, but this will eliminate the steady state error. So now I don't want to add pure integrator. I don't want to eliminate it. I want to reduce it by a factor of 10. So I want to reach 0.01 error, which is okay for me, instead of having 0 steady state error. And why I want to avoid pure integral? I want to design different controller, maybe add here some pole P, which I find now. Okay. So why, in your opinion, we want to avoid pure integrator? For many reasons. First, like pure integrator, it is numerically it's not robust enough when you do it in numerical way. When you want to numerically adding it on your controller, on your computer, it is not robust and it consumes memory too much. But however, you can add different type of integrator, not pure integrator like S plus P, 1 over S plus P, in which you can reduce the steady state error, not cancelling it, not eliminating it completely, but it has a good effect with some acceptable errors that you can reach. And this is, for example, if it's not pure integrator, S plus P, 1 over S plus P, has the advantage to be more easy to integrate. Also, analog way, if you want to design PID analogly in analog way, pure integrator is also hard to make. It's also an active circuit. However, this type of integrator S plus P could be made. We can make it by passive circuit, not active circuit. So it doesn't need external power to make it. You can make it by inductance and capacitance. But pure integrator, you need active circuit, completely op. So you consume more resources, more current, more energy. Okay, so that's why pure integrator, if we can avoid it with some acceptable error, better to avoid it. Also, it leads to instability. Of course, both they lead to instability, but it's worst. 1 over S is worse than 1 over S plus P. Also, this is a system of type 1. System of type 0. Type 0 system, or the type 0 system for a step input has a steady state error. So I know my steady state error equal to 1 over 1 plus Kp according to this table, and we know that Kp equal limit when s tends to 0 of g of s. G of s is the open loop function, transfer function, so it is limit when s tends to 0 of k 1 over s plus 1, s plus 2, s plus 10. So equal to k over 20. So Kp equal k over 20, and k is your gain, which you find it here, which is 180. So then Kp equal to 180 over 20. So 180 over 20 is equal to, okay, let's using the calculator and see. 180 180 over 20, 2 point over 20, 180 over 20 equal 6. 180 over 20 equal 9. So Kp equal 9. Then E steady state equal 1 over 1 plus 9 equal 1 over 10 equal 0.1. And this is what you find in here. This is the 0.1. Here is what you find here. 1 minus 0.9 is 0.1. The one that you found in previous exercise on the 1 minus 0.9, it to give you 0.1. We're just here to tell you like you can find the state error by calculation. Just I wanted to show it to you. So now the goal is really to find the this compensator that lead you to a new steady state error which is 10 times less. Okay, so then we need to use an integral, because we know integral will eliminate the steady state error, but I need to reduce it. So then we use lag or lead compensator. So we'll use lag compensator. So then we will use lag compensator. So the lag compensator will reduce the steady state error but doesn't eliminate it. And it has the advantage it's passive and easily integrated. It consumes more efficient numerically than an integral. Consume less memory and more efficient. Analogically, it is less. It's a passive circuit. You can make it using passive circuit. You don't need ampli op. You can use inductance and capacitors. Numerically, it's consume less resources. Easy to integrate. So, what is lag compensator? We call it lag because of the past. Like the integral. Integral is the past. Lag compensator is also the past, similar. So it has same effect, but doesn't eliminate the steady state error. It reduces it. So also reflect the past. That's why it's lag compensator. And what is lag compensator? Lag compensator, let me call it GC of S. That's what you want to design. GC of S. S plus 0 over S plus pole. And all what you need to find the 0 and pole, and therefore you get your lag compensator. Well, lag compensator is equivalent to PI controller. If you have PI controller, this is equivalent to PI controller. And okay, where to put this is a complex plane, imaginary and real. Where to put the the 0 and the pole? Here where you put the pole, and here where you put the 0. P and 0. Well, what we mean by here is just the pole smaller than the 0. Basically, the pole is what dominant the system. The pole dominant the system. That's why we call it lag compensator or equivalent to PI controller. Well, if I ask you lead compensator, lead, in case we want lead compensator, it has same effect as PD controller, and it is the future. So derivative tells about the future. So lead, that's why we call it lead compensator. And in this case, GC of S is S plus ZC over S plus PC. So it's the same then. So how they distinguish them? That's how you distinguish them. We'll see now. Real imaginary, and zeros than pole. PC, ZC. So what's dominant is the 0. So 0 is dominant or dominating the pole. 0 dominating the pole. That's why it's PD. That's why it's lead. So the 0 dominating, it's close to the imaginary axis. Here, the pole is dominant. Pole is dominant. Or pole is dominating the 0. Okay, that's the main difference in the number, how much it is. So if PC smaller than ZC, absolute value I'm talking, or ZC smaller than, closer to the imaginary axis. So this is lead, this is lag, and this is lead compensator. Lag and lead compensator. But now we don't need the lag compensator. But just to see the difference between them. But for now we don't need lag lead compensator. We only need lag compensator. Why? Because they told us they need to improve the steady state error. So what improves the steady state error is the lag compensator. Alright, so how to find ZC and PC? This is a good question. We need to find ZC and PC to get E new equals 0.01. So let me find the new transfer function now. The new transfer function, it is, if you wish, in here you have GC of S, you have the gain K, you can include it here if you wish, and you have G of S. Y minus plus alright. So now how to work with G of S is not 1 over S plus 1, S plus 2, S plus 10. K is the value that you have 180, and GC is this one. So what is ZC and PC? We need to find ZC and PC. That's at the end. Okay, that's your goal. So to find the compensator that reduce the steady state error by 1. And here is the trick. So now let me find the KP for the system, because the new steady state error, which is equal to 0.01, right, according to 0.1 over 10, so equal to 1 over 1 plus Kp new Kp. Why? Because this is JC, GC, K, G are system type 0, right? GC times K times G are type 0 system. So Kp new equal limit when S tends to 0 of the open loop system. So S plus ZC over S plus PC times K times 1 over S plus 1, S plus 2, and S plus 10. So then equal to ZC over PC K 1 over 20 equal to KP new. Then KP new, okay. So how much is KP new? KP new we can find it from this formula. (0.01), then we can find KP new. So KP new is known, K is known, equal 180. So you can find ZC over PC. So I can find ZC over PC. Okay. So here I was doing it for you. KP new was, according to this formula, 99. So then 99 I can find ZC over PC. Once you have ZC over PC, assume a pole, then get the 0. Alright, and you get then the lag compensator. The lag compensator, which is ZC and PC are known then. And basically this should satisfy your requirement. That's how to do it. I didn't use the CISO tool. Well, you can use the CISO tool, but here it's better to do it by calculation, because you will facilitate your life. You don't need to keep tuning, and you may get, you may doesn't get. You'll here. For me, I find this is faster to do it by calculation. So here is the CISO tool that we have. Maybe I can turn it off, or I keep it because the G is the one, same one we want to use. And my controller now is not 180. I want to add lag compensator. So add lag compensator. Okay, so here you have, I click on it. So they ask you for the real 0 and the real pole of your lag compensator. So the real 0 of my lag, according to my calculation now, the 0 is at 0.11, because this is ZC over PC, and I assume PC equals 0.01. So 0.01, 0.11. So this is how my system behave. I don't need help. So preferences, we have it as we said. So now this is how my system behave. Did I satisfy my requirement? Well, you need to change your gain K until you find so here if you look now to the steady state error, see 0.99, and the overshoot alright. Maybe I decrease it just a little bit, and then here is overshoot 57%. 56. So then maybe if I use 180 as the one we had before, it's 47.3. So 57.4. Compensate the system to improve steady state error if the system is operating with a damping ratio of 57.3. So then I can get it 57.3. 57, and this is at 220 for them. So when the gain K is 220, I get this compensator. Okay, this compensator then, it helps me reduce the steady state error by a factor of 10 and keeping the overshoot as per required 57%. So I put a gain of 220. So my system as a whole becomes 220 times a controller S plus ZC over S plus PC, where ZC and PC equals those 5. So basically all what I did to make sure that I'm dividing by 10 the steady state error is to get a ratio between ZC and PC equal 11. So you can assume any value for the pole and then you deduce the 0. We recommend to take the pole close to the origin because it's an integrator. So when it is pure integrator close to the origin, so recommend to take it close to the origin and then you deduce the Z0, the ZC. Alright, so that's basically my recommendation. And the advantage of it, we know it reduced, doesn't eliminate, but it seems like this satisfies the desired requirements. And why I need to use an integrator, pure integrator. Consumes memory, not robust in numerically, so create problem. And if you want analogly, an analog way to represent it, it consumes also power. Like you need to use ampli op to construct the integrator. So why I need to use, if this lag compensator satisfy my requirement, and this why lag compensator are doesn't completely reduce the steady state error, doesn't completely eliminate the steady state error, but it reduces it in a acceptable ways, and I use lag compensator better than integral. Okay, and it is equivalent, as we said, to a PI controller. Well, if you think little bit, so PI controller in the form that we know is like Kp plus Ki over S. So if I take S common, so what you get here, Kps plus Ki. So alright, so now if you take S common, for example, so if you take Kp common, then it is S plus Ki over Kp over S. Okay, so here like this is the PI, it has pure integrator, and as the exercise we did it and the previous exercise 1, in exercise 1 we had S plus 0,1 over S times K, which is came from the game, so it was PI controller, pure integral. So now it's equivalent to it, okay, but S plus 0 over S plus pole. So you have here plus pole, of course, multiply by gain K, which is here in this case 180. That's the old gain. So now the gain is 220 to reach the overshoot, desired overshoot. You tune the gain again. So then it is P. So that's why it's similar to, but it's not exactly same effect, because here you have pure integrator. So how to find the new gain? You based on okay, so if I take K in 180 now, the way if you take K180, you will get exactly 0.99. Like, you can go here, don't take it 220, take it 180. See, it is 0.99. Alright, and but overshoot is less than. So if you want overshoot of not 47, the one that is per requirement is okay. So you improve a little bit your steady state error. That's it for exercise 2. So now we saw it in as application in the CISO tool, but we was relying in the design of the lag compensator on the calculation. Basically, in this ratio is T over PC. So you need to get familiar with this type of exercise. When they ask you to reduce the steady state error, think about lag compensator, and this is the lag compensator as explained.